Why PCS1? PCS is short for Product Coordinate System. And what we will do is we will define a product coordinate system that's moving along with a belt with a part to be picked. We will just define it that it's right on top of the part we want to pick. That will be important later when we do the programming. Similarly, on the other belt, we'll have a position above where we want to place the part. And we will have the position where we place it. I call it PCS2, Product Coordinate System 2, because here also we will define a moving coordinate system on the second belt. This will allow us to do the synchronization or tracking, as it is called in our product, with the moving objects. Okay, and then we need to program the movement. So the movement will be, we move from the rest position above the pick position, move down, pick the part, move up. Then we will move to above the place position, move down, place the part, move up again, and go back to the rest position. And then we will repeat this cycle as long as there are parts to be picked and placed. So we will refer back to this overview because it helps to keep the orientation when you dive into the code. Okay, so next, let's start with the coding. And we don't start entirely from scratch because that would take too long for this hour of my talk. So I prepared some frame around the problem, but the main part is still open. So maybe let's start top down and I explain you the project. By the way, I assume that you have some basic familiarity with CODESYS and programming. I try to do it smoothly, so I hope everyone can follow. So this is a standard CODESYS project. I selected a PSC. I use a soft PSC here for demonstration. And I also have some drives. I use virtual drives here because it's a demo without real hardware. Maybe we can look at an example drive configuration. So we can see I have finite drives. I configured some limit switches. We have dynamic limits configured. We will be programming in millimeters. So 5,000, the maximum velocity here means 5,000 millimeters per second, like 5 meters per second. Similar the acceleration and the jerk. Okay. Next, we have a configuration for the robot itself. So as I mentioned, we're using this type of delta robot. Here we have some explanations about the coordinate system and parameters. This is all done already. I configured this for our setup, all distances, angles, radiuses. We also have this orientation kinematics, which allows us to rotate around the z-axis to rotate the parts, like 1 degree of freedom here. And we don't have any tool lengths for our example. And next, we have the mapping. This tells our robotics which drives are to be used to control the robot. So we have the 3 drives here for the delta, and then we have the 1 drive for the orientation. And you can see here we have 2 additional drives for the belts. And that's it. Maybe a quick look at the task configuration. There are different tasks. The interesting task for us is the robot. The other tasks are used for the simulation. I created a simple simulation that simulates the camera, the part dispensing, and so on. So we don't have to care about this. But the robot is really the part that we will be programming. Let's have a look at that. It's just a frame here. We have a few function blocks already, like group power to power up the drives, group enable to enable the access group, and some diagnostics, read status, read position, and so on. So this is just the frame. And I prepared 3 methods: enable robot, pick and place, belt 2 handling. And the one we will concentrate on is the pick and place. The other ones are finished already. They are really simple. Let's have a look. So to see there's nothing complicated hidden here. Here we just enable the group power and the group enable and wait until the robot is ready. And then we go to the state setup done. Nothing more. And the belt 2, this is the handling of the pallets. So we're looking at the environment, whether there's a new pallet where we can put our parts, and then we use this pallet. So this is also just a short program here. And the main program that's not done yet is pick and place. So it's just the initial state is programmed. We wait until the setup is done, and then we can start here, but nothing is done yet. So this is now our task, to really fill in the code for moving the robot and picking up the pieces. Okay, so let's start with that. As we saw in our diagram, maybe I'll do a quick switch back. First thing was this rest position. So I think in the beginning, we will start with moving to this rest position. And before we do the program, I create the movement function block. I go to the declaration of the robot program and create a new function block of type mScene_move linear absolute. This will be familiar to many of you. We are using PLC Open for motion control, part 4 for coordinated movements, and this is a standard function block from PLC Open for linear movements. And now we'll fill in the important parameters. So first, the position. And I've prepared this position. It's called, how's it called? Oh, sorry. See, we need to look it up here. I prepared a constant. The rest position defined in the machine coordinate system is this x0, y0, z is minus 550. So we just use this constant in the code. The function block also needs the coordinate system. Coordinate system in which this position is defined, and this is the machine coordinate system. This will be important later when we use the product coordinate systems. There we need a different one. And then we need to get maximum values for the path velocity, acceleration, and jerk. I prepared some constants for this. We can have a look in a second. I just pass it to the function block. By the way, this will be faster for the second and the next movement function blocks. We can copy this as needed for the first one. Okay, and then another important thing is we don't want unnecessary stops. So we want all the movements we have to be blending, which means don't stop at the exact positions, but blend over the positions to have a smooth movement with high pick rate. And we do this using the buffer modes and the transition modes. Here also I have a constant that we can use. I show you the definitions in a second. The transition mode and the transition parameter. Okay. So now we have configured our movement, and I show you now the value that we used. So the maximum velocity here is 5,000 millimeters per second, the acceleration and the jerk. And then we have the buffer mode, which is blending high, which means we want to do the blending. Transition mode is start velocity. This is a velocity-based blending. And the parameter 1 is like 100% blending, full blending. Okay, good. Now that we have the movement function block, we can go to our state machine into the next state. I've done steps of 10. And we can simply start this movement by giving it a rising edge on execute, and then go to the next state. So this will start the movement. What's also needed is the call of the function block itself. Call it each cycle here, and it needs a reference to the axis group, which is in our case this tripod here. So it's the same name. Okay. Now in the next state, we wait until the command has been accepted. This means just that our robotics has accepted the command. It doesn't mean it already started the command or even finished it. It's just the system has accepted it. So we have some internal like look ahead and queue, and this means the queue is the command is in the queue. And once it's accepted, we can go on. And what we do is we reset the execute because we want to repeat this cycle again later, and then we need a new rising edge on execute. So we reset the execute flag. This doesn't stop the function block. It just resets the input. The function block continues to run. And we go to the following state. And now we are at the rest position. I switch back to the picture here. Now we are here, and what we need now is we need the position of this part on the bed. So we need to wait until the camera has detected a part and determined the position. And that's what we are going to do next. And as I told you, I created the simulation of the entire environment, and the program is called environment, and it has an output. It's called object detected. And this is like the camera has detected an object. And then we have a second condition. There's an array, I call it buckets. Our pallets have 4 buckets. And in this array, we just do the bookkeeping, whether the bucket is filled or not. So if the value is true for a bucket, it means the bucket is still empty. We still need to fill it. And the environment, the camera will tell us what kind of part it has detected. There are like 4 different parts for our 4 places in the bucket. And here, this condition means we take the part only if it's the right one, if the bucket is not filled already in our pallet. Okay. So what do we do? Once we have detected this part, now what we want to do is we want to define this product coordinate system that we've seen in the presentation. This one here. We want to define the moving coordinate system that will move along with the part. And how do we do this? We have a function block for this that's called MC track conveyor belt. Tracking means synchronizing with the conveyor belt. So this function block will give us a coordinate system that moves with the conveyor belt. And I just create this function block here, call it belt 1, track conveyor belt. And we will initialize this. What we need is the conveyor belt origin. This means where in space is this conveyor belt? And we have to look it up in maybe in our diagram here. I go back one slide. And here we can see belt 1 and belt 2, and I've drawn the coordinate systems here. So we have the conveyor belt origin here at these coordinates relative to the MCS. Okay, so that's what we need here. And I also have a constant for this, belt 1 origin. Can have a look at this if you want to see it. You can see these are just the coordinates from the drawing. Okay. And we need a further thing, the coordinate system. So we want to define the PCS1, and that's what we tell the function block here. PCS1. Okay. Now we have defined the function block. We still need to call it. I go back to our state machine. We need to call it here. Again, we have the link to the access group. And second thing is we have a link to the drive. Let me look it up. Drive belt 1. So this drive is moving the belt. Okay. To fully define our coordinate system, what we do here is we set the initial object position, that's the position of our moving part, to the object position that the camera, the environment is giving us, that comes from the camera. So this is the position and also the orientation of the object. And then we just need to execute this function block, and this will configure and define the PCS1. After we have done this, we can use the PCS1. And we go to the next state. So this is really a core part of our logic. We wait until the object is detected by the camera. We then configure our PCS, and then we can use the PCS in the future. And we do this here. Once the configuration is done, and this is just a configuration, no movement is done here. It's just a configuration. It will finish like in one cycle. We reset the execute, so we can repeat the cycle later. And then we want to start the next movement. I will call it move above peak pos. So I will start this. The function block doesn't exist yet. So we have an error here. We still need to create this function block, but I will nevertheless call it already. So let's go to the definition and define this function block. And as I said, we can now copy this previous movement. We just need to modify a little bit. We don't need to type everything. Move above peak pos. We also use a move linear absolute, but we will be using a different position here. The thing is, maybe we start with the coordinate system. We will program relative to this product coordinate system. And the product coordinate system is right on the part. So the position 0 here would be right on the part. So that's almost the correct position. We just need to go up in Z direction a little bit. So what we do is we define a position x0, y0, and in Z, we go some distance. I have a constant for this in PVL, some distance above. And we have no orientation. Orientation is 0. Relative to the PCS. The PCS could be rotated, but the target position of our movement has no orientation change. Okay. Good. So let's go back to our program. Now, this is of course wrong. I need an execute. Okay. So next step. We now started the movement. Again, we wait until it's accepted. Usually it's accepted immediately. It's just if the queue fills up, if you do many iterations, it could be the queue fills up. Then we need to wait. And we again, this is standard. Reset the execute. Okay. So what do we do next? I switch back to our overview. We are now here above pick pos. Next would be to go down. Okay, so how do we program this? We could again use a move linear absolute, but it's a bit easier to use a relative movement. So we do just that. So we create a new movement for going down. I move down, and now we're using a move linear relative, which is pretty similar to the absolute, but instead of a position, we have a distance. So let me copy this because it's almost the same, and use a distance here. And we are also using coordinate system PCS1. We still are synchronized to the moving part now. Okay, and now we are going to move in Z direction only. And moving down means negative Z direction. And all other coordinates are 0. So we are moving just down. Okay. All other parameters are the same. And now we go back to our state machine and we can use this new movement, move down. And we go to the next state. Okay. Now, what we do next is, once it is accepted in state 16, we will program a wait. This is to let the gripper, give the gripper the time it needs to pick the place. This will need a few milliseconds. And therefore, wait. First to reset the execute and then start a wait. Go to the next state. Wait is a simple function block that we can add here. SMC group wait. And it just has a single parameter, a wait time. And I have somewhere I have a constant here. Let me check. Let's use the constant, the wait time in seconds. It's 100 milliseconds. Good. Okay, we execute the wait. And once it's accepted, it's the same, it behaves the same than like a movement. It's accepted in the queue. We reset the execute. And the next movement would be a move up. We didn't declare it, but I just use it. And we also set a chord system. Because the reason I do this here is I can reuse the move up and move down also for the belt 2 for the other coordinate system. We use the same function blocks but change the coordinate system, so it's a bit less code to write. And I forgot this, by the way, here. Let's do it here for move down 2. Okay. And now we need to declare this function block in the declaration part. We use the move down as a template. Use the relative movement, and the only thing we need to change here is the distance. In positive set distance, we'll move up. Okay. So now we program the up movement. What next? Now we need to turn on the gripper at the right time. So in reality, maybe we would use a digital output. In my simulation, it's just a Boolean flag that we can set. And we will do this once the move down tells us that it has reached the position, the part. So if move down has the done output set, I will turn on paper here. Turn on the flag gripper on. And go to the next state. Okay. Okay. So now we have about half the state machine. Let's go back to the diagram to keep the overview. What we have done now is we have moved to above peak, we have moved down, and we have moved up again. And I think you saw the principle, how I use a very basic and straightforward state machine. So I won't go through all the following steps because they are really similar. So we will have the movement above place, if down and up again, and to the rest pose. So what I will do instead is I will copy these states. I prepared them elsewhere and will copy them, and we just can have a short look over the code. So you can see what I've done, but we don't need to do them in that detail. So first was the code. Maybe we go first through the state machine, and then I'll add the missing function blocks later. So we wait until the move up has been accepted. We set its execute. Then we wait until the pallet has been detected on the other belt and start the movement to above the place position. Then we do the move down, and here we just change the coordinate system of the move down. Now, not PCS1, but PCS2. So the relative movement will be relative to PCS2. Then, once move down has been accepted, we perform a wait again to let the gripper, give the gripper the time to open up and place the part. And then we program this move up. And yeah, after that, once the move down is finished, so we have placed the part, we turn the gripper off. And here's the bookkeeping I talked about. We then know we have filled this bucket of the pallet. So we just set the Boolean flag for this packet to false. And for this to work, by the way, we need to remember the current product ID. But let's go to the end of the state machine first. Once the move up has been accepted, we reset the execute flag and go back to the beginning to state 10 and move to the rest position. So let me just finish this here. In state 30, when we detect the object from the camera, we just keep track of the used product ID so we can do the bookkeeping. We remember this value, that's all. And one more thing that we also do here is we configure the movement above the place position. We set the position here. And here the environment will give us the right position above the pallet. This could be another camera, for example, or the pallets could have fixed positions on the belt. So this would depend on the machine. In my simulation, we get the right position here. And we just add to the Z coordinate, we add this distance to be above it. Okay. So now we just need to declare the missing function blocks. And this would be move above place position. Just add them here. Copy it, move above place pos. It's the move linear absolute in PCS2. And what else is missing? The belt 2, the the function block for the second dynamic coordinate system. It's quite the same like the first one, just with the different origin and different coordinate system. Okay. Let me check. Do we have move up, move down? I think we have all function blocks, and maybe some of the calls to the function blocks are still missing. I go to the end. Yeah, we don't have all the calls. So let's add the remaining calls. So we have move up, we have move up, move down, and wait missing. Check. Down, move up, wait. Okay. And I think we are done with this. I think this is a final state machine we need. Let me think about it. If we have forgotten something, no, let's try it. I'll hit compile. Okay, we have an error. So seems. No. Okay. Compile went through. Good. Okay, so I would say we give it a try. I connect to the soft PLC. Log in. And for us to see something, I open this 3D visualization. This is our depictor. And start. Okay. Something is wrong. Okay, what we can see is the parts are coming. This is the simulation I was talking about. And the robot tried to pick one part, but it seems we still have a bug in our state machine. So it went off until it reached the end of the workspace. You can see it here, the drives are at their limit. And I think it will tell us, yeah, position outside of working area. Okay. So let's have a quick look in our state machine. This is not intentional, by the way, but I think it's good that I can show you. You can use all the CODESYS features, like the debugger, to debug the motion application, right? Because it's really part of the IC application. So now what we see is we are somehow stuck in state 70. Okay, and yeah, I see what I did. I just forgot to change the state here. So I log out. Add this missing statement. Once the wait has been accepted, we need to go to the following state. Okay, just a silly mistake. Let's try again. I wouldn't have done this on the real machine like this. I think it's good to test this in simulation first. But I think no damage would have occurred because the software limits have been in place, so the robot stopped in time. Okay, I'll open the visualization again. Give it another try. Okay, that looks better. So now the parts are picked and then placed to form these CODESYS logos. Okay, I hope you can see the depictor moving. On my screen, it looks smooth. I don't know how it looks over Zoom. I don't have much experience with Zoom. But on my screen, it looks smooth, but the question is, does the robot really move in a smooth way, and does it respect all the velocity and acceleration limits? So what we can do here is we can use the trace that's built into CODESYS. And I've prepared the trace so we can see the position of the robot, of the gripper. This is the first diagram. And then, maybe I blend this out, we have the velocity of all the drives of the robot. And also the acceleration and the jerk. The jerk is the derivative of the acceleration. And what we can see is the velocity is from minus 4,000 to plus 4,000, so it's in the limits. The acceleration also is in the limits. We had 80,000, if you remember, and the jerk 2 million is also in the limit. So it really moves as it should. And if we zoom in a little bit, we can see it's a smooth movement. And if we add the path velocity, you can see this is like the typical pick and place shape, this head. This is really, yeah, these are the corners of the pick. And here is the vertical, the horizontal section, sorry, where the robot can go with high speed and then it's a decelerate. So this is like a smooth trajectory for our motion. And it looks a bit different everywhere because the parts are coming in different positions. So it's not the same always. And this is, I think, the movement back to the rest position. This is the pick and place. Okay. So let's see whether it's still running. Okay, still running. Good. We could play around with this, do an override change. Maybe I can change the speed of the belts, maybe. This is the thing we can quickly try. We have this belts program that's part of my simulation. And the one belt is running with 200 millimeters per second, the other with 100. We can change it for both to run with the same velocity. I go back to the visualization, and now I'll apply the change. Now the belts should change their movement. You see now both are moving with the same velocity. Yeah, and the robot still can keep up with it. Okay. Good. So far about the pick and place and the live programming. Now let's switch back to the presentation. And the next part is a short overview of the new features. This will just be a few minutes and an outlook. So what's new since the last 2 years, version 4.16 and 4.17 roughly? A new feature is the torque limitation for robotics, which means we can limit the torques and forces of the drives, provided the user has a dynamic model of the robot. We have an interface, he can plug his dynamic model into our robotics. Another bigger feature was triggers and forecasts. So triggers for robotics, it's similar if you know in CNC the H functions, you can define trigger points on the path, and then you get notified in advance when the trigger will be reached. The forecast is a similar feature where you can give a time offset and get the path velocity and acceleration in the future. It's also useful for glue dispensing, for example, if you have a dead time. We have an override function block for basic motion. It's more a convenience feature because we supported changing the velocity at any time, but the override makes it a bit easier because you don't need to restart your movement function blocks. You can just change the val factor and it's fine. Also for the basic motion, we have a forecast functionality, similar to the robotics. You can query the velocity and acceleration in the future. And a big issue in the last release was extending the MC Chem in. We did quite a lot there. We have a new segment type, poly 7. Before we only had poly 5, and now we have polynomials of degree 7. Then we have a new cam builder API. This is an API to create cams in your IAC application. Before this has been possible, but you had to fill in an internal data structure, and it was not really convenient. And now we have a nice API. So it's much easier to create cams in the application. And then we have distance-based ramping in for MC Chem in. It's also a feature that was requested often. It works the same like for gear and POS. Okay, drive support. We have a few new drivers for the Mitsubishi Mel servo, for WEG, for CMZ, and also for the Bosch Rexroth Control X drive. So this is, I would say, business as usual. We are getting new drivers every year. Okay. Now, regarding the outlook, I'll keep this short. In summary, we want to bring together the CNC part and the robotics part and combine the advantages. So the CNC has the property that you can define the path, the geometry very precisely using G-code. But on the other side, our CNC solution doesn't take into account the limits like velocity and acceleration and jerk limits of the axis, or torque limits. And on the other hand, the robotics can consider all these constraints like the axis limits and torque limits, but it doesn't have this fine-grained control over the path. Usually, like we've seen, you do wire points and blending. So what we want to do is combine them. We want to make it possible to use our G-code and execute the path with the robotics. So you'll have advantages of both together. Okay, so as a short recap, what I've shown you is that CODESYS of motion turns a PLC into a powerful motion controller. Next, we have seen how easy it is to program pick and place with tracking with CODESYS of motion. And I've shown you that we have added a lot of valuable features in the preceding years to CODESYS of motion. So it's really an active development. So that's all from my side. Thank you for your attention. If you have any questions,